Assalamualaikum. My name is Mio Sazman bin Yusuful Bahrim, and today I will be presenting a study titled Interatomic Potential of the Magnesium Aluminium Interface and its Application in Strengthening Mechanisms. Let me begin by introducing the background of this study. Aluminium is widely used in aerospace, automotive, and structural applications because of its lightweight and good conductivity. However, its mechanical strength is limited, especially when subjected to stress and deformations. To overcome this, ceramic materials like magnesium aluminate are added to aluminum to form metal matrix composites. Magnesium aluminate is known for its high hardness, thermal stability, and low density, making it ideal reinforcement. When combined, the interface between magnesium aluminates and aluminum becomes critical importance because it governs how stress is transferred, how discolorations move, and ultimately how strong the composite becomes. However, despite knowing the magnesium aluminates improves the composite's properties, the atomic scale mechanism at the interface remains poorly understood. That's why this study used computational simulations to investigate how atoms behave at the interface, especially during mechanical loading. One of the central challenges in developing strongest aluminum-based metal matrix composites lies in understanding how interface between the metal and the ceramic reinforcement behave the atomic scales. In this study, the focus is on interface between magnesium aluminates and aluminum. It is already known that adding magnesium aluminates improve the mechanical properties of aluminum, such as increasing its strength and stiffness. However, the exact mechanisms by which this strengthening occurs, especially the role of atomic interactions and dislocations at the interface, are not fully understood. Study this interaction requires molecular dynamics simulations, which can handle the large atomic system and simulated deformation behavior. But MD simulations depends heavily on accurate interatomic potentials, mathematical models that describe how atomic interacts. Without this, any simulations result will be unreliable. While first principle DFT-based methods can produce highly accurate interatomic data, they are too computationally invasive to apply directly in the large scale MD simulations. On the other hand, MD is efficient but lack accuracy unless supported by fixed interatomic potentials. At the time of this research, there were no validated interatomic potential models for the magnesium aluminum interface. This made it possible to perform relative atomic scale simulation of how the interatomic behave under mechanical stress. Therefore, the problem this study addresses in the lack of accurate, practical, and validated interatomic potential parameter for magnesium aluminum's interface. Filling these gaps is essential for the enabling large-scale simulations and for revealing the true nature of strengthening mechanism at the interface. This study aims to address key limitations in simulating the magnesium aluminum interface. The absence of validated interatomic potentials models. The primary objective is to develop a set of accurate, efficient, and practical potentials parameters that can be used in large-scale molecular dynamic simulations. To achieve this, the first goal is to generate new interatomic potentials for aluminum oxygen aluminum-magnesium and aluminum-aluminum interactions. These are derived by fitting classical potential functions, specifically the Morse and Buckingham models, to high accuracy energy curve calculate from first principle methods. Once the potentials are fitted, the next objective is to validate the accuracy by comparing them to the FP results. This step ensures the fitting models accurately represent the real atomic interactions. Finally, the validated potential are applied in MD simulations to study mechanical behaviors of the interface. The simulation aims to uncover how the interface respond under tensile loadings, how dislocations form and evolve, and how when the thickness of the aluminum magnesium aluminates ceramic layer affects the composite's mechanical performance. This objective collectively support the broader goals of revealing atomic scale, strengthening mechanism, and improving the design of high-performance aluminum composites. In this study, a multi-step computational methodology was applied to investigate the atomic scale strengthening mechanism at the magnesium aluminates aluminum interface. The process begins with principal calculations to generate accurate energy distance curve for the atomic interactions, especially aluminum oxygen, aluminum magnesium, and aluminum aluminum. These curves were essential for the understanding how atoms interact across the interface. Next, these curves were used to fit in the atomic potential functions for the use in molecular dynamic simulations. The Morse potential was applied to the aluminum-oxygen interactions due to its strongest and partially ionic nature, while the Buckingham potential was used for aluminum-magnesium and aluminum-aluminum interactions, which are more metallic and repulsive, which the fitted potential parameters. The research teams constructed 5 different interface models, each with the different thickness of the aluminum-magnesium aluminates layer 10 angstrom, 20 angstrom, 28 angstrom, 36 angstrom, and 44 angstrom refer to the T10 to T44. Following this, molecular dynamic simulations were carried out using the LAMPPPS software package. A uniaxial tensile loads was applied in the directions Z, while the bottom's atomic layer were fixed to simulate the relativistic boundary conditions. To analyze the mechanical response, several tools were used. This includes the dislocations extraction algorithm DFA to identify dislocations structures, von Mises screen to visual location plastic deformations, and polyhedral template matchings PTM to identify local atomic structure like FCC and HCP regions. This comprehensive methodology enabled the teams to simulate the analyze how variance in the ceramic thickness influence dislocations, activity, and strengthening behavior at the atomic level. The first results from this study involves variation the accuracy of the fitted interatomic potentials. Figure 1 compare the first principle DFT data with the fitted energy curve for 3 atomic interactions: aluminum-magnesium, aluminum-aluminum, and aluminum-oxygens. For aluminum-magnesium and aluminum-aluminum, the fitted Buckingham potential curve closely match the DFT reference, capturing the correct repulsing behavior at short distance and decay at longer range. For aluminum oxygen, the most potential was used, as these interactions is strongest in partial ionics. The most fits accurately followed the deepest energy well of the DFT curve, indicate the strongest bonding. The successful fitting validates that the choice potential replacement real atomic behavior accurately. These validated parameters are then used in all subsequent molecular dynamic simulations. Next, the mechanical scattering effects was evaluated through the tensile test in MD simulations. The results show that adding a magnesium aluminate layer significantly increased the material's flow stress among all models T28 and which a 28 angstrom thick ceramic layers produce a highest flow stress, showing a 203% increasing compared to pure aluminum. The atomic scales mechanism behind this strengthening was explored using a dislocation analysis. Simulation revealed that stay roots dislocation formed at the interface. This dislocation is immobile and adds strong barriers blocking further dislocations movement across the interface. This is what causes observer's strengthening. Thus, the combination of thickness and dislocation blocking effects explain the improvement in mechanical performance. In this part of the study, the effect of the magnesium aluminate layer thickness on mechanical behavior was investigated using the 5 interface models T30, T20, T28, T36 and T44 represent increasing ceramic thickness. The results show that T10 and T20 which thickness magnesium aluminate layers allows more dislocations motions across the interface. This leads to lower strength but highest ductility. On the other hand, T28, T36 and T44 as highlighted highest flow stress means strongest materials. However, this also appearance reduced plastic deformations indicates a trade-off. The T28 models give the best balance. It achieves the highest flow stress with a manageable amount of ductility. This highlights the interface thickness is a key design factor. Thinness layer improving ductility but reduce strength, while thickness layer increasing strength but limit deformations. Designers must choose the right thickness based on whether strength or flexibility is more important. In conclusion, this study successfully developed and validated new interatomic potential parameters for the magnesium aluminum interface. By fitting Morse and Buckingham potential to first principle energy data and applying them in a large-scale LA-MMPS molecular dynamic simulations, the teams were able to realistic simulation mechanical deformations and dislocation behavior at the atomic levels. The simulation revealed that first, thinner magnesium aluminum layers increase flow distress by impeding dislocation motions. Second, the 28 models 28 angstrom thickness provide the most effective balance of the strength and ductility. Third, the formations of immobile steroids dislocation at the interface is a key strengthening mechanism. Overall, the reveal provides valuable insight into atomic scale strengthening mechanism and offers a validated simulation framework for designing highest performance aluminum composites reinforcement with ceramic light magnesium aluminates.